much. I mean, thank you very much also to the organizer. I've been told to do something to wake you up. And, I mean, during the vacation, somebody might suggest it's like a long-distance flight. I mean, you have very little leg room in the cheap places, and it's a long day, but slowly, I mean, in a little bit more than an hour, we'll have touchdown. But I have to say, as your captain, somebody's now taking over who just doesn't understand anything. People were talking about the first incompleteness theorem, second incompleteness. I have no idea what it means, so prepare for a bumpy ride. To make things worse, I mean, there are people who were able to lead us. Named Georg Kreisel. I mean, he had these great ideas, and he led us to great insights and mathematically fruitful results. And I mean, this talk is, I mean, dedicated to Georg Kreisel because I'm going to say something about results he obtained in the early 1950s. However, I do not really know whether it's such a good idea to refocus on this part. That's what I did. Because Kreisel actually regretted having written that paper. He told me. So Kreisel wanted, I mean, to go in mathematically fruitful directions. And this was a paper that Kreisel had almost killed off an extremely fruitful development, namely Löw's theorem, provability logic, and so on. And I'm going to talk about that paper, even though Kreisel thought it's a dark corner where strange things happen, but it's, of course, where philosophy lives. So I'd like to drag you into this dark corner, and maybe you also come out as confused as I feel now. Okay, so I have to say this is joint work, to some extent joint work with Albert Visser. We have two papers in the RSL. It can also be downloaded as one single paper. We are now working on something on coding, but I should say Albert doesn't agree with what I'm saying, at least philosophically. But of course, Albert is always extremely good at answering formal questions. So, but the philosophy is my own. And I mean, for those of you who asked me for the slides, or if you want to read the slides right now on your own computer, they are on my website. So if you go to my Google my name, my website, left column at the bottom, talks, and takes you to this PDF. Okay, so this talk is about self-reference in arithmetic, or more precisely about sentences that ascribe to themselves certain properties. You might think maybe that's only a metaphorical way of talking, but this is how we very often describe, say, the first incompleteness theorem, Henkin sentences, and so on, by saying this sentence states about itself that it's not provable or that it's provable. And this, I mean, goes back to the most famous of all persons having written on that. Namely, Gödel himself said about what has come to be called the Gödel sentence: we thus have a sentence of arithmetic before us that states its own unprovability. And I would like to understand what this means. I mean, it's a very long arithmetical sentence. To what extent does it really say about itself that it states that it's unprovable? Okay, I'll keep formalities to a minimum. I will need a theory for arithmetic. It should be sound, so definitely not, say, the negation of the consistency statement or something like that. For different results, I need different strengths. For most of the talk, Q would suffice, but later on I might actually need quite a lot of induction, and even I sigma 1 wouldn't suffice. So you're always allowed to think of sigma as a piano arithmetic, of course. Okay, now I'll give you more examples about self-referential sentences. First we had, I mean, the Gödel sentence. I mean, I call this the intentional version of the first incompleteness theorem, because the first incompleteness theorem just states any sufficiently strong system of arithmetic is incomplete. And that is not intentional. I mean, it just tells you the sentence is not provable, but also its negation is not provable. But as soon as you look at what is expressed by the sentence that is constructed in the proof, then things become more complicated. And that's what I'm interested in. So, I mean, Gould showed that the sentence described on the previous page is not provable as the sense that states its own unprovability. And I'm wondering whether the formal results actually support this claim. You might already be wondering whether it's okay to use a singular. That's, I mean, at the core of the thought. There are many different sentences stating their own unprovability. But what I have in mind is maybe in natural language there is this sentence or canonical sentence, a sentence that says, I'm not provable. But of course, if we model that in arithmetic, there are many choices we will have to make. And so in the formal language, there will be many such sentences. Coming back to that later. Then, of course, a very natural move is, I mean, Gödel told us what happens with the sentence that states its own unprovability. What happens with the sentence that states its own provability? That's Henkin's question. And Loeb is supposed to have answered that question by saying, well, it's provable. That follows from Loeb's theorem. Then, if you don't look at provability, of course, we can multiply questions. You could ask about Rosser provability, for instance. I mean, it's clear what happens here, but the Henkin sentence for Rosser provability is completely up in the air. But what got me thinking about these issues are truth-teller sentences. I'll say more about that later, but very roughly, in arithmetic, we can define truth predicates for a set of sigma n sentences, and then form truth tellers, and they are truth tellers for sigma n truth. How they're constructed, we'll say more about that. And you could wonder what happens to these sentences. It feels a little bit like thinking about Henkin's problem before Loeb came up with his solution. And, I mean, it's mainly Albert proved that the sigma n sentences, the sigma n truth tellers are refutable. And not very surprisingly, the Pn sentences are provable. And we think these are the correct answers, but this will need many qualifications. In particular, I mean, we will have to be much more precise about what it means to say stating its own sigma n truth. Okay, and we can look at many other predicates. Okay, I mean, in order to construct such sentences that ascribe to themselves a certain property, we usually proceed in 3 steps. So take any logic textbook containing an account of the first incompleteness theorem. What are the steps you take to construct a sentence that states its own unprovability? First step, fix a Gödel coding. So we, somehow define a function that takes expressions of the language and returns natural numbers. This is actually a little bit tricky because we want to say this is somehow a computable function, but of course it takes syntactic objects and returns numbers. So it's not, the kind of function we deal with in recursion theory, and to say the syntax is coded and then we define a recursive function won't do. We really need to go from expressions to numbers. Then the second step will be, and that's of course a very complicated story, we pick a formula that expresses the property we are interested in. So in the case of the first incompleteness theorem, that will be non-provability, which will be the negation of provability. So in particular, how do we express provability in our chosen arithmetical system sigma? And there are again many choices. Then in the final step, once we are given a provability predicate, we will have to construct a self-referential sentence. And of course, the standard way to do that is using the standard Gödel diagonal construction. Substitution of numerals. You know the trick. Okay. Now, at all 3 steps, we must make choices. So in particular, in the first step, we have to choose a coding. There are many different codings. What makes a coding a good coding might depend on your sigma. If sigma is very weak, you might use a coding where the codes don't grow too quickly. But usually, people just choose one particular coding. And it would be indeed very strange. For instance, if say, the first incompleteness theorem, its intentional form, or also the second incompleteness theorem, depended on a particular coding. Of course, we all know it doesn't depend. But nobody, I think, as far as I can tell, has really given a thorough account of what that means. Oh, yeah, we could have used another code. Then, of course, in the second step, that's, I think, fairly well investigated. I mean, once you have fixed the coding, depending on that coding, you define a formula expressing the property you are interested in. So, you, for instance, you define a provability predicate, and that is what Pfefferman investigated in his famous 1960 paper on the arithmetization of meter mathematics. He was not interested in, I mean, the different choices that he could make here. He just fixed one coding. He was also not interested in intentionality of self-reference. That was not his main focus anyway. So that's well investigated. I think this and this is a blind spot to some extent. Okay, so this gave me the idea for the following research program. If we really want to show that this result, the sense that states its own unprovability, is not provable, if that should have any force, we should not only prove it for one particular coding, we should show that the result holds for all reasonable codings. Maybe it's not so hard to prove that once you have fixed the notion of a reasonable coding, but explaining what a reasonable coding is not so easy. One might say we can approximate and make some guesses. At the moment, I'm working with Albert on this, and we are struggling. But something can be shown. Then, of course, we want to show it for all reasonable codings, but we also want to show it for all reasonable choices of formulae expressing property P, so all good provability predicates. Again, here we might rely a little bit on Pfefferman, but actually when we look at his construction, he was mainly interested in the consequence. When are we able to prove the second incompleteness theorem? But we'll have to give criteria of what are reasonable choices of provability predicates, and then show for all of them the sense that expresses its own unprovability is not provable. And similarly for all the other results. For partial truth predicates, we also will have to give a criterion for what makes something a good truth predicate. And very interesting, we should also be able to show this for all choices of constructions for self-reference. There's not only the canonical Gödel construction for obtaining self-reference. Actually, it's at the moment, I guess, completely unclear what self-reference is, and that's at the core of the talk. Yeah, and if we cannot do something like this, then of course I have the feeling, oh yeah, the sense that expresses its own probability is provable by Luke's theorem. Does that say anything if you just prove it for one particular coding, one particular choice of the provability predicate, and one particular method for getting fixed point perhaps? No, we want to have something more general. And that's what I'm making some remarks on that. And some of these remarks are a little bit skeptical. Okay, so I'm mainly concentrating on self-reference, but of course all these different dimensions of intentionality interact. So of course when you tweak the coding, you have to change your provability predicate and the self-referential construction. So saying I keep the provability predicate fixed and I keep the self-reference construction fixed and just change the coding is already very difficult to tell what that could mean. Okay, and first I look at provability and then at the truth tellers. Okay, so I think when all these problems really started to become appreciated and when people first thought about self-reference in a more serious way was when Henkin asked his famous question, what's nowadays usually dubbed as well the sense that states its own provability. But Henkin was actually fairly careful. He did not ask what happens to the sense that states its own provability. Because he did not really want, I guess, simply to assume it's clear what self-reference is. So the formulation might look somewhat convoluted, and I'll try to make explicit what he really had in mind. So maybe for the moment you can postpone that and then go back. But for the moment being, think of that as an attempt to ask what happens to the sentence that states its own provability. A very natural question after Gödel had shown, well, the sentence that states its own unprovability is not provable. This is where Kreisel enters the scene. So he answered basically a stupid question. It depends on how, which formula is used to express provability. So if you choose this provability predicate, you get a provable Henkin sentence. If you use another provability predicate, you get a refutable Henkin sentence. Actually, don't go into this dark corner, nothing will come of it. That's of course why Kreisel, regretted having written that paper. There's no mistake in it, but it was, pointing people in the wrong direction. And it seems Loeb did not really pay much attention to the Kreisel paper. He just went ahead and proved his theorem. Fortunately, he didn't listen to Kreisel. Okay, so, in order to give an answer to that question, now we are following Kreisel and look at Kreisel's answer, because I think he even misdescribed his own result. The first step will be, I'm not going to say anything about the coding for the moment being, so we have one fixed. And now we need to say what is a good provability predicate. And Kreisel adopted the following criterion for what makes something a good provability predicate. And it's basically weak provability, weak representability of provability. So what we want is, if your chosen theory sigma proves phi, then sigma proves that phi is provable. And this is, of course, the numeral of the Gödel code of phi. So if a predicate satisfies this, then it's a good provability predicate. That's, of course, fairly weak, but back at that time, Kreisel thought that's okay, and of course, that's what's needed in order to prove the first incompleteness theorem. For the first incompleteness theorem, it's not required that BW satisfies further conditions. Of course, the second incompleteness theorem is a different story. Okay, so let's say any provability predicate weakly representing provability in sigma is a provability predicate. Okay, now we come to the more delicate business of self-reference. So what we want is a sentence that says of itself that it's provable relative to a chosen provability predicate. We call it a Henkin sentence. And I think the first requirement is the formula should be a fixed point of the probability predicate. And of course, if you look back at the first incompleteness theorem, when you carry out the Gödel trick, the self-referential construction, all that is really needed is you need a sentence gamma that is provably equivalent to not provable gamma. I'll skip the bar to make things easier. Once you have this, a fixed point of non-provability, the proof goes through. You don't need anything else. So it's clear that in order to be a sentence that says about itself that it's provable, it should be a fixed point of provability. But as we'll see, that's very easily satisfied. And I'm also very confident that Henkin realized this would not have been a good question to ask what happens to formulae that are fixed points of provability. And this is because, first, just the requirement that something is a provable fixed point doesn't narrow down the set of sentences that are potential candidates for being self-referential. So first we could say, what about the set of sentences that are fixed points of phi in the standard model? This set of sentences is not arithmetically definable. And this is just a variant of Tarski's theorem on the undefinability of truth. So assume you have a formula that defines the set of fixed points, then you have a formula chi, but then you rebracket associativity of biconditional, and then here on the left-hand side you have a proof predicate. So okay, there's the set of fixed points is not definable, and that holds for any old formula whatsoever. So the set of fixed points is always a very complicated set. But of course we are more interested in provable fixed points in the set of all psi, such that phi of psi fin only psi. And again, for any old formula, the set of psi's has the maximal possible complexity. Of course it has to be recursively enumerable. That's just because it's defined by a provability. But it's also not recursive. So, I mean, just saying fixed point doesn't really narrow down, the class of formula that are possible candidates for self-reference. That is already a hint. We should be looking for something more restrictive.
But is it a necessary condition?
It's a necessary condition, yes. Yeah. Right. Okay. And in the specific case of provability, of course, we definitely have, say, some tautology or trivial arithmetical proof, sigma proof 0 equals 0. Then because we have weak representability, we also have this. And that implies, of course, completely trivially, because both are provable, zero equals 0 is a fixed point. Therefore, asking what happens to fixed points of the provability predicate is not very interesting. This sentence is definitely not a self-referential formula. I'm just emphasizing that because very often in the true theoretic literature, people say, let the liar be a fixed point, and then what happens? No, just being a fixed point of something doesn't imply that it's a self-referential sentence. That's, one thing. So you have to find additional criteria for self-reference. And Kreisler and Henkin actually came up with a criterion. They did it very specifically for provability, but I think it's fairly clear that what they had in mind is something like this. This is the official formulation, but I can give so a formula phi x expressing a certain property p, so that's our provability predicate, that's given. And now we're interested in a formula gamma that expresses that gamma has the property expressed by phi. And how did we get that? Well, it has to be of the form phi of t, where t is a closed term, and for some closed term, t that has the code of phi t as its value. So we must have this in the formula, and then if you can prove this, then phi of t is self-referential according to this criterion. And I think that makes sense, because phi says, well, t, the object denoted by t has the property phi. But of course, t is probably identical to phi of t. So from this we get, of course, the fixed point property, and we have a term that denotes the sentence itself. So that's what people call this self-reference. Of course, there is a minor problem with that, which is not so minor. Namely, if you are in a language that lacks function symbols. So, usually t could, for instance, be the usual Gödel construction. But that requires that you have function symbols for certain primitive recursive functions. That's not a problem, but if you are in PA, then this, criterion would actually say there's no real self-reference in Peano arithmetic, because you have only plus and times, perhaps. Unless you change the coding, then you might get self-reference again. Also in the language of set theory, you don't have any closed terms, so there would be no self-reference. Somehow my hope is, we know how to add, function symbols as definitions. Maybe we can then say something about self-reference via quantification. But for the moment being, let's focus on self-reference obtained via closed terms in the language. I think that's hard enough. And of course, I mean, there's a general way to do it. If we have this usual Gödel term, substitution of blah 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 by the numeral and so on, then we get such a closed term here. That's of course what Henke and Kreisler are after. Okay. Just a side remark. I mean, actually, you can, even if you have a language of arithmetic that contains only, say, 0 and the successor symbol as function symbols, no plus, no times, no function symbols for other primitive recursive functions other than the successor, then you can actually get self-reference. And you can get self-reference without proving the diagonal lemma. And you can do it in a uniform way. This is something Albert observed in his old paper in the Journal of Philosophical Logic on the liar paradox. So you fix a very sophisticated coding. Then if you're given a formula phi of x, then you can effectively find, it's not so hard, a number n such that phi of n has Gödel code n. And of course that's provable in sigma. So your term t is actually a numeral. So this is not a complicated term that notes itself. No, I mean phi of n has code n. And so if you prove the first incompleteness theorem via this funny coding, you don't have to prove the diagonal lemma in the language. I mean, that gives you everything you need. I have the feeling there's something very fishy about it. That's, I mean, actually a fact where this intentionality comes in. You can pull this trick only with a very specific coding. And if you use that method to prove the first incompleteness theorem, somebody could say, well, that works for this specific coding, but if you used, say, a normal textbook coding, it wouldn't work any longer. And then you would probably have to say, yeah, sorry. So when I say the sentence that says about itself that it's not provable, it's not provable, that holds only if you use Albert's very clever coding, but not the Kini coding or whatever. But nevertheless, it's really clever. Okay, so now what did Kreisler do? So we have now fixed this, notion of self-reference, the Kreisler-Henkin criterion. And what Kreisler did, he showed, well, I can get a sentence that says about itself that it's provable, that is provable, and I get another sentence that says about itself that it's provable, which is refutable. And the two sentences are this sentence, this one is provable, and this one is refutable. Now, what are the other things we have to prove? These are, the conditions for expressing provability and the conditions for self-reference. So, let's look at the first formula. We have a provability predicate, BW1, and a term T1, such that the following is satisfied. Well, first, BW1 is a provability predicate, according to Kreisler's criterion of weakly representing provability. Provable 1 T1 is self-referential in this sense. So it's self-referential, and it's provable. Okay, this won't surprise you. Probably know Gödel's theorem. Having a provable Henkian sentence is not so surprising. If you keep everything canonical, that's what you get. But of course, Kreisler didn't have Gödel's theorem. But what's more surprising is you get also refutable Henkian sentences. Exactly the same, this time it's refutable. And the interesting thing is, of course, both of these provability predicates that Kreisler constructed are non-standard provability predicates. But in order to get the term T2, he did not apply the standard diagonal construction to this provability predicate. He pulled a trick. So this is, and if you apply the standard diagonal construction to this predicate, actually get again a provable Henkian sentence. So we actually exploited two things, using a non-standard provability predicate and using a non-standard way of obtaining self-reference. Okay, and in order to explain the trick that used for self-reference, I do something completely informal. and it's kind of a puzzle. So you have a sentence labeled A, and A says about, A is the sentence, A equals A. Okay, this sentence probably says about itself that it's self-identical. I mean, A says A equals A, so A says A is self-identical. Does the sentence say that it's identical with A? Somehow, yes. So it will ascribe to itself at least two properties. Namely, first the property of self-identity. A says of self that it's self-identical. Okay. But does the sentence also ascribe to itself the property of being identical with A? I'll leave that for you to decide. Most people say yes. But now I'm showing you another sentence that also says about itself that it's identical with A, that is actually false. I mean, this one is clearly true, trivial by identity logic. But what about that sentence? A sentence B, and B is B equals A. I mean, B is clearly different from A, so that's a false sentence. But in a sense, it also seems, well, B says that I am identical to A. But this time it's false. So if you think they both express I'm identical to A, then one of these sentences is true, the other one is false. And this is basically the idea Kreisel exploited. And I'm not sure whether, you share these intuitions. But if you follow the Kreisel-Enkelin criterion, then they both say about themselves that they're identical to A. Okay, I'll now give you the formal proofs, which are not difficult. Actually, this is not really the original Kreisel proof. Henkin wrote a review of the Kreisel paper and then suggested simplifications. And these are Henkin simplifications. And this is the provable Henkin sentence. Again, we know Lip's theorem, we don't need that proof. We know that anyway, that there's such a sentence. But actually, the construction of the sentence that is refutable is, very, very similar. Okay. Everything looks very standard, it's just the wrong order. So, first, we fix a provability predicate. Need not be the usual provability predicate. Any old predicate weakly representing provability will do. But it can also take the standard provability predicate. Then you pick a term, T2, such that this is provable in sigma. And you can obtain such a term, T2, by using the usual Gödel construction. Looks like this, just with a little bit more complicated condition up here. And then, after having applied the diagonal lemma, only now you define the provability predicate, which is this. So this is the sentence. You drop T2, replace it with a free variable. You drop T2 here again, replace it with a variable, but you keep T2 here. So this says X is distinct from T2, and it's provable in the usual sense. Something went wrong. Usually you would expect for the construction of a Henkin sentence, first to define a provability predicate, then you diagonalize. It's the other way around here. Okay, so, and this is now actually our Henkin sentence, the refutable Henkin sentence. The refutability is completely trivial. T2 distinct from T2 and something else, refutable, sure. What we have to show in order to get this, we have to show that the provability predicate we have defined is actually a provability predicate, i.e. weakly represents provability, and we have to show it self-referential. The self-referentiality, is trivial. We get this. This is self-referential because, this is a provability predicate. So what remains to show is that it actually weakly represents provability in sigma. So let's say we have sigma proofs phi. Then, we get, I use a definition. We have phi it's T2 and provable for the original proof predicate of phi. That's what we want to show for weak representability. And if phi is any sentence distinct from this sentence here, then of course that's satisfied because you can forget about that conjunct. But if it actually is T2, if it is that sentence, then it's not distinct from 2, and this is refutable, but the sentence itself is, as we have seen, refutable. So both sides are refutable. So it is a provability predicate. Okay, so what we have shown is there is a refutable Henkin sentence. Okay, now when Henkin wrote the review, one has the feeling it was frustrating. This is not really what I wanted to know. This is cheating, and it's cheating because Kreisel had used a contrived provability predicate. Yes, true. I mean, this is very contrived. But also, something went wrong with self-reference, because what we had expected was, here's the provability predicate, apply the standard construction with, then you get the sentence that says about itself in the sense of this predicate that it's provable. But if you do that, you get a provable Henkin sentence again, not a refutable one. So Kreisel messed with the probability predicate, but he also messed with self-reference construction. Of course, Kreisel could say, well, I mean, what you asked for is something that satisfies the Kreisel-Henkin criterion. You didn't ask for anything else. You did not say the sentence that is obtained by the usual Gödel construction. And I think it would have also been a little bit weird if Henkin had asked, I will pick a provability predicate and then we apply the usual Gödel construction and then we got something self-referential. Because I think, yes, the Gödel construction is one way to obtain self-reference, but after all, it's a trick. And self-reference should not be, defined by a very specific trick. It's something else. But if you have just the Kreisel-Henkin criterion, well, then this is self-referential. I find this puzzling. Okay. And, Albert and I discussed it. Maybe it comes from an old paper by Smorinsky, who observed there is something going on, but it's just one sentence. So, Kreisel exploited two dimensions of intentionality, representability of provability, and self-reference. Okay, and this is what I have here. We have refutability as before, but if we apply the standard diagonal lemma, we actually get the standard provable Henkin sentence. So if you think the Kreisel-Henkin criterion is not sufficient for self-reference, you might say Kreisel didn't show anything. This is the way to get self-reference. And then Kreisel would have failed. And Kreisel never commented on it. He always just said, well, it's about how provability is expressed, not how we get self-reference. So there's very little discussion about that. And this made me think, actually, we should really have a good criterion for self-reference. Yes, the standard Gödel construction gives us self-reference, but how can we tweak it, and what's still self-reference? And I'm still puzzled. And I'm also puzzled because in the literature on truth, people fight each other because they disagree on whether the Diablo sequence is self-referential or not. But the notion of self-reference is completely up in the air. Gray and Priest basically said, well, you're using the diagonal lemma to get the Diablo sequence there for self-reference. It's not clear to me at all. So I think they apply completely different standards for self-reference. And even in, the most controlled context, like Henkin sentences, it's very hard to say what self-reference is. Okay, so this is the upshot. So it depends also on self-reference. Self-reference is intentional. And that. I think the reason why people didn't really think about different ways of obtaining self-reference is that if you focus on standard provability predicate, textbook provability predicates, or in general provability predicates that satisfy the loop derivability conditions, then all fixed points behave in the very same way. Okay, that's what we have got here. So in particular, we get, maybe I should say what Lüb proved in 1954. If the system is sufficiently strong, if you have this, then it follows that phi is provable. So in particular, if you have a biconditional here, it's just a fixed point of provability, then phi will be provable. And therefore, all Henkin sentences are provable equivalent because they're all provable. So intentionality from self-reference was completely erased in the case of provability, where provability is expressed by a formula satisfying the derivability conditions. And that is what people focused on for doing provability logic. And yeah, I mean, also for Gödel, I mean, all the Gödel sentences are provably equivalent. But that is, for that you only need the fixed point property. You don't have to talk in any way about self-reference. Okay, so, I mean, everything looks fine for provability in a sense. I mean, if you know what a canonical provability predicate is, which we don't, but I told you it will be a bumpy ride. Okay, before we proceed to other predicates different from provability, I would like to show, well, actually you can prove what Kreisel promised to prove. So you can define a provability predicate, provable Fisser X, with a provability predicate, and then you apply the usual diagonal construction to it, and you will get a refutable Henkin sentence. And you can also get an independent Henkin sentence. So you get everything using this standard diagonal construction. Of course, the provability predicate is even a little bit more contrived. But I haven't got that much time left, so I'll skip the proof. Yeah, we have to talk about the truth tellers. And they are harder.
Just 8.
Okay. I think we have covered this more or less. Okay. So in the case of provability, everything looks maybe still manageable. But I would like to emphasize that canonical provability is a very, very special case because we get Lüb's theorem. If we consider other predicates, I don't know, Rosser provability, for instance, cut-free provability, partial truth predicates, and so on, we cannot expect to get Lüb's theorem, and therefore different fixed points may behave in completely different ways. And when we then ask, well, what happens to the sentence that states its own Rosser provability? No idea. And different fixed points of that predicate may behave in highly different ways. Okay, so I think in order to give answers to the kind of question we had at the beginning, we have to have an answer, an approximation to what it means to be self-referential. And maybe Kreisel-Henkin is the best shot we have got. Of course, it's also clear that there are questions of the self-reference kind of sense that ascribes itself to property P that can be highly, highly intentional if we look at syntactic predicates. I mean, just as a caution, when you have, for instance, the property, you have a sentence that says, I have an even code. My Gödel number is even. Of course, when you change the coding, the truth value will change. You can also change the truth value by using a different construction for self-reference and so on. That's highly intentional, but that's actually not interesting. So what I thought might be more interesting is truth. Sorry. Okay, so that's how I got there. In a sense, I felt like in a time machine. I was wondering what about the sense that states its own sigma 1 truth, and I felt like Kreisel Oh, that depends on how you do all the crazy subtleties. But back to the beginning, what is a truth predicate? So, I mean, I'm here making use of this complexity classes very, very roughly. Say sigma 1 formula is one where you have just bounded quantifier and just one unbounded quantifier at the beginning. Pi 1 is one unbounded universal quantifier at the beginning. Sigma 2 is one unbounded existential, and then an unbounded universal quantifier, and so on. Very, very roughly. Defining that in some detail is also not completely trivial. And then I say for a truth predicate for the set of sigma n sentences is a formula that proves the T sentences, but of course not for all formulae, but only for those of a limited complexity. Say they have only one existential quantifier. It's a sigma 1 truth predicate. Okay, then there's a result. You can define such a sigma for each sigma n, and the amazing thing is the sigma itself is again sigma n. So you don't have to use a higher complexity. So of course, if you now constructed a liar sentence, then this gamma would be the negation of a. So let's say we are interested in we have a sigma 1 truth predicate. If you now constructed a liar sentence, you can get that using the diagonal lemma. But then, of course, this gamma is the negation of a sigma 1 sentence. It's pi 1, basically. So it's not the right truth predicate. So we don't get, of course, we don't get a liar paradox in pure arithmetic. These are purely arithmetical predicates. But, I mean, we might apply the diagonal lemma to sigma, and then just sigma, not the negation of sigma, and then we get a sentence gamma that will itself be again sigma 1. So it's a truth teller. I mean, it's a sense to which this can be sensibly applied. So we can formulate truth teller sentences. Okay. Then, and of course, truth behaves, of course, in a completely different way from provability. I mean, for provability, we had all the fixed points behave in the same way. They're all provable if we fix a canonical provability predicate. Clearly, this is not the case for truth, because take two very simple sentences, 0 equals 0 and 0 is distinct from 0. They are both fixed points of the sigma 1 truth predicate, but clearly they are not equivalent. So different fixed points, I mean, behave in different ways. So what we want is self-referential fixed points. Okay, and then using the tricks we learned from Kreisel, we obtained results on truth teller sentences that say of themselves that they are sigma n true. So there's a truth predicate sigma x, and that's a truth predicate, say, for sigma 1. So that the truth teller formulated with sigma n using the standard diagonal function d, I mean that's the usual way to get the fixed point, is refutable PA, but it's provable with another construction for self-reference that still satisfies the Kreisel-Henkel construction. Basically what we did, we played Kreisel's trick and then showed, I mean, if we get the fixed point via the Kreisel trick, we get a provable get a provable truth teller, and otherwise we get a refutable one. So we can see the way we diagonalize can influence whether truth teller is provable or refutable. Of course, the truth predicate, they satisfy the T sentences, but they look a little bit weird. Now you might ask, what's the criterion for a good partial truth predicate? Actually, I don't know. I mean, you might say, I mean, Leon talked about it. Yeah, we have the T sentences that makes them good truth predicates, but perhaps also the compositional axioms. I mean, at least for sigma n formula, the conjunction is true if both conjuncts are true, and so on and so on. Actually, sigma could also satisfy all these additional conditions up to sigma 2, n of course. So that's not the problem. And we get this also for more conditions on the truth predicates. Everything you want. Okay. So actually, you could still use provability. There is the standard formulation of partial truth predicates for sigma 1. But what I find confusing is if you work, say, in piano arithmetic, and you have the sigma 1 provability predicate, that's a sigma 1 truth predicate. This is because piano arithmetic proves. So actually, it's not important. Say this is a subsystem of a sufficiently strong subsystems of PA. We get this. This is because, of course, we get this direction already in I sigma 1. It's formalized sigma 1 completeness, and we get the other direction because piano arithmetic proves the reflection principle for this system. So now I'm wondering, is this a good good truth predicate for, sigma 1 at least? I don't know. They behave completely different from the usual partial truth predicates for sigma 1. Okay, we'll get that there in a sense, in a moment. Yeah, and then we can simply get this effect not by exploiting intentionality from self-reference. You can also get it just by tweaking the partial truth predicates. So the truth teller sentences are intentional in both dimensions. Intentionality from self-reference, by tweaking self-reference you can get different results, and by tweaking the definition of the partial truth predicates you can get diverging results. The problem is I would also like to prove by changing the coding, whatever that means exactly, you can get diverging results. I think that can be done, but I'm seriously struggling. Okay, that doesn't show it's difficult. Albert doesn't know how to do it. That's, more worried. Okay. What we did is, and that's, Graham Lee was also involved, is what we can do is we can say, keep everything canonical. And canonically is just defined by Hayek-Pudlak or some other textbook. You might want maybe Richard K's textbook. So we use textbook definitions of the partial truth predicates. We use standard Gödel diagonalization, and we also use a standard coding. And then all the sigma n truth tellers will be refutable, and all the pi n truth tellers will be provable. But I don't know really what that means. It's so highly intentional. Just keep everything standard, and that's defined by textbooks. Something is weird. And suddenly, for instance, also what comes in, we have to exploit specific properties of the coding. For instance, what we need is if you have the numeral of a number in an expression, then the code of that expression must be bigger than that number. So monotonicity properties, usually satisfied in standard codings. But you don't need that for the incompleteness theorems. But here you need it. So truth tellers are just highly, highly intentional. Wherever you, change something, things blow up and things behave in different ways. Okay, so this is the best result we have. We don't know what it means. Okay, so it depends on everything. Okay, so maybe, I'm addicted to these axiomatic truth theories, as you know. So I just can't keep myself from commenting on that. Richard Hack and a simplification by Thomas Schindler have claimed that, for instance, this axiom, true, non-true t, where t is a closed term, if and only if not true t, is inconsistent only if you have suitable function symbols in the language. Of course, what they mean is we have the function symbols for substitution and the numeral function. And so that depends on the language. Okay, that's a dimension of intentionality. I've not really mentioned the language. It's there, but put that under the carpet. But actually, in order to show that this is inconsistent, it's also intentional with respect to other things. Even if you have just successor and 0, this becomes inconsistent if you choose a crazy coding. Namely, Albert's coding, where phi of n has code n. So you can take things in different directions, and you can tweak results by changing the coding, self-reference, and so on. And I mentioned this already. What's worrying is that I used to think I know what self-reference is, but when you think about, say, Yablo's paradox, you really need clear criteria for self-reference. And the best we have got is the Kreisler-Henkel criterion, but it doesn't exclude this really weird tricks that Kreisler had first applied in 1953. So this is stuff to think about in the future. Okay, so what to do about these things? Okay, so in the case of Henkin's problem and the intentional version of Gould's first incomplete system, so provability, there's a reasonable hope that we can prove these invariance results I mentioned at the beginning. So all the sentences with a reasonable coding, a reasonable formula expressing provability, and actually we don't need that. A reasonable self-reference will behave in the same way. And that is because all fixed points behave in a reasonable way. We don't have to analyze self-reference in order to get a result. But in other cases, such as truth tellers, things look more challenging. There's no uniformity. You change a little bit here, get a different result. Change a little bit there, still a different result. And I think it's a pity that the entire analysis or the project of analyzing self-reference was killed off by Lüb's theorem, where suddenly all the fixed points behaved in the same way. That's good for provability predicate, but it doesn't help us, for instance, with partial truth predicates and truth tellers. It probably doesn't help us with, say, Rosser provability. I have no idea what happens there, and so on and so on. So examples can be multiplied, and we have no idea what self-reference in arithmetic really is. We should perhaps, I want to close on a skeptical note. When people say, oh yeah, this sentence says about itself that it's sigma n true or something like that. And I say these things all the time. Actually, I have no idea what I mean. So, I told you. Touchdown now, but I don't know whether you still feel safe. Thank you.
About the last slide with the naive input. So you say, well, perhaps we should remain skeptical about the possibility of representing self-reference in arithmetic.
Yeah.
But is another way to go to be skeptical about being able to express partial truth in arithmetic and say, well, we have. But that's not quite the same thing as self-reference.
Yeah,
because could you just say, well, truth is a primitive notion. It's truth.
Then you can define a truth predicate that satisfies your axiom for truth, at least for the sigma n sentences. And whatever axioms you give me for truth, at least for sigma n, I can do what you expect from that truth predicate. Yes, by saying we have not really a good idea what self-reference in arithmetic is, doesn't imply that we have a good idea of how to express sigma 17 truth in arithmetic. Yeah, I remain skeptical, and also with respect to coding, I don't know what a reasonable coding is. At the moment we think a reasonable coding might be defined as a coding that relatively interprets a certain syntax theory. That would be our guess. And then, for instance, we might be able to get our sigma n truth tellers refutable if you keep everything else canonical. So yes, I mean everything is up in the air.
You made some quite critical remarks of the discussion about self-referencing in the Diablo paradox. Am I right in having the take-home message that discussion is really a bit of a waste of a time until they pin down what one means by self-reference?
Yes, I mean...
that's a harsher way of putting it.
Yeah. I mean, for instance, just saying, oh, we need the fixed point theorem or the recursion theorem in order to produce the Diablo series of sentences. I think that won't do. I mean, we have seen there are many fixed points of predicates, but they're not self-referential in any way. So probably we have to fall back on something like the Kreisel-Henkin criterion for self-reference. And something like that might be done. But very often in this discussion I have the feeling people just, discuss and it's completely unclear what they mean by self-reference.
Yeah, on this exactly. So you're not happy with what Hannes tried to do in his 2002 paper, trying to understand what self-reference is you're still, it's not good enough for you.
I'm not happy with that. But we're still friends.
Yeah. Why? What's missing there?
I mean, it's a highly complicated notion there, and so I think, I think there are examples where I just intuitively have the feeling he gets self-reference, and I would say actually no. But yeah.
So it's an extension of dynamics.
My suspicion. But I mean, there are just many different methods out there to make that case. What self-reference would be. 100?
Is there any other question? Oh, yes, sir.
I'd just like to indulge in a little personal recollection. My teacher in logic was Hilbert and Gentzen. Actually, early stage of his career. And he was very skeptical about the whole idea of self-reference, and in particular about the claim that the usual Gödel sentence says of itself that it's not provable. I think he was led to this by some remarks by Wittgenstein and some such source as that.
Okay.
But maybe all the problems you've encountered about giving a proper characterization of self-reference gives him some posthumous vindication.
Yes, I think that might actually be the case. I mean, maybe being there a little bit more cautious might be a good idea.
Another recollection connected with this, I think I recall an occasion when I saw a predicate. This would have been probably no later than the early 60s. Protested against this view and said, well, I could perfectly well have a proper name inserted in a sentence about which I could stipulate that what it stood for was that very sentence. That's maybe not that relevant to actually, except it does come up in one of the tricky codings that you mentioned.
I mean, this is exactly I think the idea. So n is identical to the code of phi of n. Kripke firstly likes this. We stipulate possible worlds, we stipulate that names refer to, and actually you don't have to use, proper names. You can do it in arithmetic using numerals. So it is possible, even in just arithmetic. I wish that. So what we have at the moment is, I mean, first you need to say that, say, a reasonable coding must take an expression of a syntax theory still to be specified.
That's the other source of intention.
Yes, of course. To a number. This function must be computable, but we have no idea what computable means in that context, because it takes syntactic objects and maps them to numbers. And then, I mean, also, concatenation should then be mapped to a number theoretic function that corresponds to concatenation on this specific coding. So if this works, then we might be able to show. Okay. Do I have to count? Syntax theory. Now we go in number theory, sigma, but this is, say, coding 1, coding 2. But because this is computable, we get an isomorphism between these two, and this isomorphism should be definable within arithmetic. If all this works, and there is one possible gap, then for instance we would be able to prove that the second incompleteness theorem is invariant under coding, which would be nice. I mean, you have this feeling, I mean, up to a certain point you code, but after that you don't use the code. Yes, there's one exception. Namely, when we have the numeral function that takes an expression and gives you the numeral of the code, then the codes come up here again. And then getting this isomorphism right. But I think you get it.
Just a short question. You mentioned a couple of times that a function that goes from syntaxes to numbers, you don't know really how to deal with this, why it should be computable, and I don't know if I understood it correctly. And but we can use the symbols for creating numerals. So we could use just another basis. For then it becomes homogeneous, at least your function becomes homogeneous, and you could then either reading them as expressions or reading them as numbers.
I mean, we are worried. I mean, it's not so easy, because of course we can say, oh yeah, we can rewrite. I mean, somehow any formula given in standard notation, just using, say, a notation with one symbol, strings of strokes, and then we have the numbers. But there are different ways to do this rewriting, but that's already coding. So again, I think it's highly intentional, and I think we do have an intuitive notion of computability on expressions, and not just, I mean, strings of strokes, but expressions in general, as long as the language is, I mean, not too crazy. And in the case of arithmetic,
I think we're done. Other questions? So, thank you.